All right, so I just want to go over a few general notes about projectile motion. There was a lot of information in the book, but I just want to emphasize a few things. So the first thing is that we are going to ignore air resistance and any interaction other than gravity. So that's going to have some ramifications. The second thing is that I know that whatever is being thrown or kicked or shot or whatever is going to land on the ground. And when it lands on the ground, its velocity is going to be zero, yes. But just as we did in previous sections when we dealt with free fall motion, we're never actually calculating what the velocity is when the object lands. The object landing involves a collision. We do not have the physics to talk about collisions yet. So when a problem asks you to find the final velocity, it always means right before the object touches the ground. There is never going to be an acceleration in the x direction. We can have situations where there is acceleration in the x direction, but then it's not projectile motion. So ax will always be 0. And then finally, the acceleration in the y direction is only going to be due to gravity, and it's always going to point down. Whether that's positive or negative depends on the way you've set up your axes, okay? So in general, projectile motion involves an object that leaves the ground or someone's hand or their tennis racket or whatever with some velocity, v0, at some angle, theta 0. And then that object is going to move through the air. And it makes this arc as it goes through the air. So these different orange circles are the same objects at different points of time. Okay? So of course, we can resolve v0 into an x component. So we've got v0x and a y component. So we have v0y. And then let's talk about what happens to these vectors as the object moves through space. Now remember, we can treat the horizontal and the vertical directions separately. And what do we know about the motion in the horizontal direction? Well, it's not going to change because there's no acceleration. So that means that my object is going to have that same v0x component the whole way through. And as I just said, of course, over here, when the object is landing on the ground, we're talking about the instant right before it lands. Okay? The vertical velocity, on the other hand, is going to change. It's the same as if I threw an object up in the air and it came back down. So on the trip up, that velocity is going to be smaller. So notice that I'm labeling it Vy, not V0y. I can label all of the horizontal velocities V0x because they stay the same. But the V0y is going to get smaller. And up here at the top of my trajectory, what's Vy going to be equal to? Well, just as it was when my object went up, stopped, and came back down, that vertical velocity is going to be 0. And then on the trip back down, my Vy's are going to be negative, and they're going to get bigger and bigger. Okay. Now, throughout all of this, we know that there is an acceleration that points down. So I'm always going to have this AY vector. And as we know from free fall motion, it's always going to have the same length, and it's always going to point in the same direction for my whole trip. Okay. So the last thing that I want to talk about is how we find V0x and V0y. So remember that I have my V0 here, and then I have V0x, V0y, and the angle between my original velocity vector V0 and the horizontal is theta 0. So we know that V0x and V0y are the components of V0. So we can use all of the information that we learned in the last chapter about resolving vectors. So again, so that we can remember, I can take advantage of the fact that I have a right triangle here and say that cosine theta 0 is going to be adjacent over hypotenuse, or V0x, over the magnitude of V0. And if I turn that around and solve it for V0x, I get the magnitude of V0 times cosine theta 0. And I can make a similar expression for sine theta 0. And that, of course, is going to be opposite over hypotenuse. So that's going to be V0y over the magnitude of V0. And again, that's going to lead me to V0y is the absolute value of V0 times sine theta 0. I would not memorize these. I would memorize how to get them, because the angle could be defined in a different way. Maybe the angle is going to be defined from the vertical instead of the horizontal. So it's always best to draw your triangle and really look at the angle and look at what's labeled so that you can determine what the components are. Now, one more point that I want to make is to note that we are using here theta 0. If the y component of the velocity is changing, then the direction of the velocity at any given point is changing as well, which means that that angle is changing. So at some time later, remember, my V0x is going to be the same. But if Vy is smaller because my object is rising up, here's going to be my V, and you can see that this angle here is going to be smaller than what my original angle is. So just make sure that when you're finding the components of V0 that you're using theta 0, but remember that that angle is going to change. All right, have a good day. Thank you.